Section 9.5, Linear Equations. A first-order linear differential equation is one that can be put into the form dy dx plus p of x times y equals q of x, where p and q are continuous functions on a given interval. So we just have our dy dx, our derivative, plus some function of x times y equals some other function of x. Notice that this equation is not necessarily separable, because if we subtracted p of xy from both sides, then instead of having a product of a function of x and a function of y, we have a sum of a function of x and another sum of a function of x times y. So it could be separable if this guy is not relevant, but otherwise, in general, it will not be separable. So we need some other way to solve this type of differential equation. So if we write this in the form of y prime instead of dy dx plus p of x times y equals q of x, then the notation might help us realize that this is basically almost the product rule. We have a function over here, we have its derivative over here, we have another function over here. So if this function was the derivative of some other function that was on this side of, well, on next to that term on the left side, then this would basically match the product rule. Because let's say we had, how about this, if this was like g prime and there was some g times y, then we'd have g times y prime plus g prime times y, and then we'd just be able to go backwards and use the product rule in reverse. So the question is, how could we make this look like the product rule? There's some missing piece that we need to multiply by, which is really like almost like the antiderivative of this. So in order to figure out what that missing piece was, let's just suppose that it even exists. We can call that function, how about I of x? And that means that I'm saying that if I take I of x and I multiply it by both sides, so I multiply it by y prime plus p of x times y, and I multiply it by q of x. But I'm just going to forget about the q of x for a minute, because I only want to try to turn this into the product rule, and I don't really care what function of x it equals, because I could always, well, almost always just integrate that myself. So let's just look at the left side for now. So if I multiply the left side by the integrating factor, keeping in mind that I would have to multiply the right side later, I can expand the left side, and I could hopefully potentially figure out what this function that I'm multiplying by is. So remember, the idea is that this thing multiplies by this and turns into the product rule. So it turns into I of x times y prime. The idea is that if I take I of x times y and I take the derivative, then I end up with I of x times y prime plus I of x p of x times y, where I of x p of x would have to be the derivative of I of x in order for this thing to actually be the product rule. So how about we expand the left and the right? So if I expand the left, I get my function that I'm multiplying, not adding, I of x times y prime plus I of x times p of x times y. And on the right side, that would have to be equal to I prime times y plus I times y prime by the product rule. So I expand this by distributing, and I just apply the product rule over here to get the derivative. This is all assuming that there is some function I that I can multiply by to make this equation even true in the first place, which is basically just what we're trying to, muddle around with, and then hope that, we can figure out some formula for I. So this leaves us with I of x times p of x equal to I prime, because on the left side I have I of x times y prime, and on the right side I have I of x times y prime. So then I can just divide by y, and I end up with I of x p of x equal I prime. So now this is a separable differential equation. I have a derivative, we could say like di dx, and I have I of x times p of x, a product. So how about I separate this by grouping together the i's on one side and integrating. So over here, I'll write it as di dx. I'll multiply both sides by dx to get rid of the dx, and I'll separate it by writing di over I, because I'll divide by I after I separate, and I'll integrate p of x dx. So integral of 1 over I is just ln of the absolute value of that. And we just have the integral of p of x, whatever the heck that is. So then I can take both sides and take them as an exponent on e. So raise both sides to e in order to get rid of the ln. That'll cancel on the left, and I just have I. And I'll have a plus or minus in order to get rid of the absolute value, but I can incorporate that into the constant because I'll just have ae to the integral of p of x dx on the other side. Because remember, when we integrate, we'll end up with a plus c, but then we'll have a plus c on e, so that would be e to the c, and e to the c is just simply a constant we can call the a, as we've seen before. So this implies that if we multiply the left and right sides of our linear differential equation by this integrating factor I, where I equals some constant times e to the integral of p of x dx, then we should end up transforming our left side of the equation into the product rule, because this entire time we're working on the left side, and then we'll just be able to work backwards. So because it doesn't matter what a is, the constant will disappear when we take the derivative anyway. So we might as well just choose a convenient number for a, so we'll just choose a equals 1. And then, in general, we'll come up with this theorem, which we essentially just proved, that to solve the linear differential equation y prime plus p of x times y equals q of x, we'll multiply both sides by this integrating factor, e to the integral of p of x dx, and then we'll integrate. Oops, I forgot an r over there. Integrate. Let's do an example of this. It should become more clear with practice. So we have dy dx plus 3x squared y equals 6x squared, which is definitely a first order linear differential equation where p of x is equal to 3x squared and q of x is equal to 6x squared. So we should be able to solve this by multiplying by our integrating factor. I of x is the integral of p of x, and then raised to the e, so we have e to the integral of 3x squared dx. But the integral of 3x squared dx is just x cubed plus c. Again, we don't need the c because we're going to take the derivative anyway, so we might as well just choose a convenient value for c. We'll choose it equal to 0. So we'll just say that our integrating factor will be e to the x cubed. So now we'll multiply the left and right sides of our differential equation by e to the x cubed, and we'll hope that everything works out, which it will. So we have e to the x cubed times dy dx plus 3x squared times y, but I'll just throw in an e to the x cubed in between, because I'm multiplying everything by e to the x cubed. And that means on the right side I have 6x squared times e to the x cubed. And you might say, well, you just made this thing a whole lot worse. You didn't make it any better. However, I actually made it tons better, because now I have some function. I have its derivative over here. Notice by the chain rule, the x cubed would hop out and become 3x squared. So I have a function, I have its derivative, I have another function, and I have its derivative. So this is just the product rule applied to e to the x cubed times y. Every single time you solve one of these, you're just basically going to be looking for the product rule after it's been applied, and you're going to be going backwards to write it as the product rule before it was applied. Notice that if I take the derivative of this, it really does work out. I get e to the x cubed. I get the derivative for y. And then I get the derivative of e to the x cubed, which is 3x squared e to the x cubed. And I just get y by itself. So then this must equal 6x squared e to the x cubed. So now I can integrate both sides. Taking the integral will cancel out this derivative by the fundamental theorem of calculus, so I just have e to the x cubed y equal to 6x squared e to the x cubed dx. Well, actually, taking the derivative, it's not really fundamental theorem of calculus, it's just the fact that an antiderivative, by definition, is an indefinite integral. The fundamental theorem of calculus is the other direction when we take the derivative of the integral. But, just, semantics at this point. Let's just say e to the x cubed is equal to this integral, which is equal to 2e to the x cubed plus c. So you can get that using a quick u substitution, right? Just let u equal x cubed, then we got e to the u, and then du is 3x squared dx, and then you just do your quick substitution, and you end up with 2e to the x cubed plus c. So that means that if we divide both sides by e to the x cubed, we get y by itself, and we've solved our differential equation. So we get y equal to 2 plus c times e to the minus x cubed. That's the same thing as c over e to the x cubed. Because when we divide by e to the x cubed, we cancel out this guy, and we just have to divide this guy. Let's find the solution of the initial value problem x squared y prime plus xy equals 1, where x is positive and y of 1 equals 2. So how about we divide everything by x squared in order to make this thing look like our linear differential equation that we want. So we end up with y prime plus 1 over xy equals 1 over x squared, where x is positive. And yep, that's definitely our linear differential equation form that we wanted to. So now we just have to figure out what our integrating factor is. So I of x will be equal to the e to the integral of the function that's being multiplied by y. So that's just integral of 1 over x dx. So the integral of 1 over x is ln of absolute value of x, but we don't need the most general antiderivative. We can just assume that this plus c is 0, and because x is positive, we don't need the absolute value. So e to the ln x just becomes x. So we'll multiply everything by x. We get x times y prime plus y is equal to 1 over x. But x times y prime plus y, this is a derivative of a function over here. And notice there's an invisible 1, which is the derivative of x. So this is just the derivative of x times y. You can test that. Here's the x, here's the derivative, and here's y. So that's 1 over x. So we just did the product rule in reverse. So now we integrate both sides. We get x times y, because it gets rid of our derivative, is equal to the integral of 1 over x dx. And that's equal to ln of x plus c. Again, no need for absolute value because x is positive. So now we can divide both sides by x to get y by itself. We get that y is equal to ln of x plus c over x. And we were actually supposed to solve the initial value problem, so they told us y of 1 is 2. So since we know that y of 1 is equal to 2, we can plug that in, and that'll tell us that 2 is equal to ln of 1 plus c over 1. So that means that this is equal to just c, because ln of 1 is 0. So we get that 2 is equal to c. So that means that we can rewrite this as y equal to ln of x plus 2, because now we know what c is, over x, assuming that y of 1 is equal to 2. Well, right off the bat, this looks like a linear differential equation. We've got y prime, we've got 2 of x times y, and we've got some function of x. In this case, it's the constant function 1. So how about we just go straight to our integrating factor? I of x will be e to the integral of the thing times y, so that's e to the integral of 2x dx, which is equal to e to the x squared. So now we have e to the x squared times y prime equal, oh sorry, I almost forgot, we still have a plus 2x e to the x squared times y, and that'll equal e to the x squared, because we did multiply everything by e to the x squared. So then we've got e to the x squared, so that'll go in here, and we have the derivative of y. So we have e to the x squared y, and we take the derivative of that, and that is the product rule. So that equals e to the x squared. So now we take our antiderivative, and we have e to the x squared times y equal to the integral of e to the x squared dx plus c. So that means that we can divide and get that y is equal to e to the minus x squared. It's the same thing as 1 over e to the x squared. And we have the integral of e to the x squared dx plus some constant times e to the minus x squared. It's the same thing as c over e to the x squared. So this is as good as we can get it, because remember, e to the x squared does not have an antiderivative in the form of elementary functions that we're used to. It's integrable, but we can't actually express the integral in any other form at the moment. So we could either just leave it like this, but sometimes you might see it written as something like this, where the integral is written as a definite integral from 0 to x, and then the variable is changed to make it more look like it's the integral itself is a function of x. But it doesn't really matter, they're both the exact same thing. Over here, when you choose your lower limit of integration, you can actually choose any number. You don't have to choose 0, it doesn't matter. Suppose that in the simple circuit of the figure, the resistance is 12 volts, the inductance is 4 henries. If a battery gives a constant voltage of 60 volts and the switch is closed when t equals 0, so the current starts with I of 0 equals 0, let's find I of t. So we did this already in section 9.3, but let's do it again, because notice that this differential equation was L times di dt plus R times I equals E of t. That's separable, assuming that E of t is constant 60. So I'll show that to you. We have L equals 4. We have R equals 12. And we have E of t is constant 60. So our differential equation becomes 4 times di dt plus 12i equals 60, where I of 0 is 0. And that's as we've seen before. So we end up with di dt plus 3i equals 15. the way that we solved it last time was by realizing it was separable because there were no t's floating around. So we were able to express everything in terms of I and then just put everything on one side and integrate. However, notice that not only is this separable, but this is linear. So we can multiply by an integrating factor here. Notice that integrating factor will have to be e to the integral of the thing times I, which in this case is 3. So how about we take e to the integral of 3 dt, which is just e to the 3t when we take the integral. So we'll multiply everything by e to the 3t. We end up with e to the 3t times di dt plus 3e to the 3t times I equals 15 e to the 3t. So now we'll just do the product rule in reverse as we keep doing. But you get that this thing is really the derivative in disguise of e to the 3t times I. And now we'll take the antiderivative and we get that this is just e to the 3t times I, and on the right side we get the integral of 15 e to the 3t, which is equal to 5 e to the 3t. So we can divide and get I of t by itself, and we get that I is equal to, I'll write I of t because we just basically solved it, is equal to 5, because the e to 3t cancels when we divide, plus c divided by that, so I'll do c times e to the minus 3t. But we know that I of 0 is 0, so how about I put that in here? I of 0 equals 0, so that means that 5 plus c, because when I plug in 0 that just becomes 1, so 5 plus c is equal to 0. So that means that solving for c, we get that c is equal to minus 5. So we have I of t equal to 5, and how about I just factor out the 5, because there's a 5 over here and there's a 5 in c now, so it'll be 5 times 1 minus e to the minus 3t. Let's find the current after 1 second now. So all I have to do is just plug in 1. So I of 1 is equal to 5 times 1 minus e to the minus 3, which is about 4.7 amps, 4.75 amps. And the limiting value is the same as we got last time. We just take the limit as t goes to infinity of I of t, and it's equal to the limit of 5 times 1 minus e to the minus 3t, which is 5 minus 5 times the limit of e to the minus 3t, which is 5 minus 0, which is 5. So we got pretty much everything the same as we did before. We found the same I, we found the same limiting value of the current, we just solved it a different way. We're only able to do that though because our e of t happened to be constant 60. What if e of t was actually some other function of t? Suppose there was a generator that was providing a different current. A generator providing a different voltage, e of t. So suppose the resistance and inductance are the same, but instead of the battery we use a generator, it provides a variable voltage e of t equals 60 sine 30t volts. Let's find I of t now. So we have 4 times di dt plus 12i is equal to 60 times the sine of 30t. So solving for, well, just expressing this in our form that we're used to for linear differential equations, we have di dt plus 3i equal to 15 times sine of 30t. So our integrating factor is still e to the 3t. So we multiply everything by e to the 3t. And we end up with a pretty similar thing to before, except that now it equals 15 times e to the 3t times sine of 30t. So on the left side, it again just becomes the derivative of the product e to the 3t and I. And on the right side, we're going to have to integrate this mess, it looks like. So we integrate both sides, we get e to the 3t times I equals the integral of 15 e to the 3t times sine of 30t. So that's pretty horrible. It's a product of an exponential function and a trig function. Looks like we might be able to do integration by parts. However, this is probably something that's in our table of integrals, so let's see if we can find it there. So we look up our reference pages. We got to go down and look for products of trig functions and exponential functions and integrals. Bunch of trig functions, but no exponentials yet. Here we go. Exponential and logarithmic forms. Looks like number 98 is an exponential function times sine, and it equals this mess. So how about we use that formula? It looks like we can just say that we've got e to the 3t, so a will be 3, t will be u, and we can write out what this is going to be. So by our formula 98, this is equal to 15 times e to the 3t over 909 times 3 sine 30t minus 30 cosine 30t plus c. And that's by formula 98. So that means that we can divide and get I by itself. We get that I is equal to 5 over 101 times sine of 30t minus 10 times the cosine of 30t plus our constant times e to the minus 3t. We're actually supposed to solve this though using the initial value I of 0 equals 0, so we have I of 0 equals 0 telling us that minus 50 over 101 plus c must be equal to 0, because when you plug in 0 for t, notice that sine of 0 is 0. So you just end up with 10 times the cosine of 0, which is just 10. So you get minus 50 over 101, and then this just becomes 1 when you plug in 0. So now we know that c is 50 over 101, so we can write I of t is equal to 5 over 101 times the sine of 30t minus 10 times the cosine of 30t plus 50 over 101 times e to the minus 3t. So you could see that having a variable voltage makes things a lot more complicated.